I shall do the recording. Okay, yeah, started already. Okay, let's wait. Okay, let's carry on with this. So this is a supplement A for chapter 5. Again, you should be able to get this in the spectrums. In fact, I have also uploaded another one. So I'm not sure whether we need to use it. So we have another set, chapter 5, supplement B. So again, is also in Spectrum. I have also uploaded in Spectrum. Right, Spectrum. Okay, so you may get it over there. Okay. Okay, so there are two. Okay, let's come back to this. The first part of chapter 5. So which regarding to all the different modes of convergence. Okay, we have actually briefly discussed these different types of the convergence. Okay, so maybe just put it over here. Just that is, we have 5 types of it. So type number 1 will be a convergence in distributions. Okay, so we will just simply denote it by D. Okay, so the second one will be convergence in probability. So we just simply represent P, use the symbol arrow P. And the third one will be almost everywhere, almost surely or almost everywhere. So we use a shorthand AS. And number 4, this is just we just simply call it L1 or the first mean, and the second one, so L2 or quadratic mean. Okay, so we are using L2 or QM. Right, so we have these 5 of them. So in distributions, in probabilities, almost surely, L1 or and L2. Okay. Of course, they do have some other types of the convergence, which we are not going to discuss in our course over here. We will just look at these 5 of them. Basically, the one that we are concerned more will be in distributions. Okay, almost surely. Okay. Right. So before we recall the criterion for all these modes of convergence, so let's look at the relationship among these 5 types of the convergence. Okay. So please remember this diagram. So QM, convergence QM always implies convergence L1, and convergence L1 always implies convergence P, and this one always implies convergence in distributions. And the reverse true provided the limit is a constant. Here means C is a constant. Okay, so this is true provided the limit functions or limit random variable is a constant. Random variables. And okay, so this is sort of like out of the sequence here. So convergence almost surely implies P. So there is no direct association between AS and QM, as well as AS and L1, right? So of course they do have intersections, but they are not mutually exclusive. Okay, so here's the relationship among these 5 of convergence. Right, so just briefly look at the criterion for these different 5 different types of convergence. Okay, by the way, just to let you know, where is the location for all these conditions? Well, just to let you know, equation number 9 or condition 9 is actually from, where should I put? Okay, maybe I put it here. So 9 is actually definitions 5.1.1, the first definitions. Okay, so the condition 10, so which is actually from proposition 5.1 point 1. Okay, so at least you can see which part in the lecture note that I'm referring to. Okay. Okay, so the next one will be this convergence in probability. So the condition 6, which is actually definitions 5.1.2, appears in definitions 5.1.2. And condition 1, so this is appeared in definitions 5.1.3. And so this is in propositions 5.1.2. And next one, so this is in corollary, not corollary. Okay. Propositions 5.1.3. And then, okay, both of these two are from definitions 5.1.5. So at least you can see where to search for these conditions in the lecture notes. Right, so for today's lecture, first part for today's lecture, so we will focus on the proof of this. Okay. So in okay, maybe I would say so today's, okay, maybe I shall. Okay, so maybe I would say section 1, part 1. So I would discuss the proof of propositions 5.1.2. Okay, so that is, I want to explain why condition 1 is equivalent to condition 3. So this is the first part for today's lectures. Okay? And the second part, so we will carry on to another sections. Okay, so I'm not going to look at this anymore, so you guys can look at the lecture notes for it. Okay? So I will focus on the first part, the convergence almost surely. I think as well as I think another one, maybe another one together with propositions 5.1.3. Okay, so that means I will focus on this and this. Okay. So this and this are equivalents, and these conditions always implies one of this. Okay. Okay, before we look at the proof for this proposition or result, so we need to recall some properties over here. Okay, first of all, let's recall this from calculus. Okay, so first of all, let's recall some concept from calculus. So I suppose you guys have already studied this thing in calculus. So when we look at the limit for sequence, so if we have a sequence xk, so we said that the limit for the sequence xk is equals to x. So this is equivalent to say that okay, I'm going to use a mathematical symbol to represent the statements. Okay, So limit for xk when k converges to infinity is equal to x if and only if for every epsilon greater than 0 that exists a natural number n such that for every natural number that is larger than n, so we have this xk minus x greater than less than epsilon. So this is the, we can say this is the criterion for xk converge to x, or limit of xk equals to x when k approaches to infinity. Okay, so we can actually replace this epsilon with 1 over m. Okay. We can replace epsilon by 1 over m. Okay, so m is of course same as this. Okay. Can replace epsilon with 1 over m. So that means you can actually put this one as 1 over m. So that's this is an equivalence statement over here. Okay, again, some of you might have forgotten the meaning for all the symbol. So maybe just to let you guys know. Okay, over here, this symbol means for every, okay, or to stand for all of them. So another symbol, so this symbol means at least one of this. Okay, so that's the meaning for this. Okay, next thing we have to look at here. What is the relationship of this and set theory? Okay, what is the relationship for these two things and these two? All right, so just let you know the answer first. What you can say is, you may say in a way you can say for all is equivalent to say that this. Okay, so when for all can be represented by intersections, and that exists in a way you can say it can be represented by union, right? Okay, so why is that so? Because of from the perspective of set theory, intersection will representing n, and union representing all. Okay, so A union B means in A or in B. Okay. So having these two ideas in mind, so then we can actually see how to link these two concepts together. So before that, so just record it. This represents for every, okay, whereas this symbol that exists represent at least one of the things. So how to interpret these things? So maybe what you can do is you can look at just look at these statements. You see, if you look at for every one from A, B, C. Okay, for everyone from A, B, C. So maybe everyone everyone among, I mean, among, okay, among A, B, C. Okay, for everyone among A, B, C. So this statement said that these three persons, A, B, C, are all involved here. So which means this is actually equivalent to say that A and B and C will be get involved with that activity. Okay, so that's why this is represented by N. Okay, this is, you can just in terms of logic, you can see it for every. Okay. Likewise, so if you look at it, at least one of A, B, C, at least one of A, B, C. Okay, maybe you can say at least one of A, B, C is greater than 0. Just for example, at least one of A, B, C is greater than 0. So which means at least one of A, B, C is greater than 0. So which is actually equivalent to say that A greater than 0 or B greater than 0 or C greater than 0. Okay, so I don't know which one are greater than 0, but here saying that at least one of them, so that means either A greater than 0 or B or C greater than 0. So this is how we can link this concept or to with this terms of at least. So again, as I say, in the perspective of set theory, so the terms or represented by union, the terms and is represented by intersections. Right, so that's the idea for it. Okay, let's come back to this sentence once again. So let's have a look at it. Right. So now you get the ideas ready. So for all, so which is actually related to N, that exists related to unions, and for all will be this. Okay. So from this idea that we can express this in terms of a collection of the outcome or set. So that means we can say that the set of outcome omega whereby limit of xk omega is equals to x, so which is equals to, okay, so this is intersections. Okay, maybe I use a red color thing. Okay, never mind, I can say. So the intersection for every epsilon greater than 0 unions for every natural number n larger than 1 and intersections for every k larger than n with these conditions. Right, so this is how we can get the statements over here. Alternately, you may just remember we have these statements over here. Okay, so this is how we can have these statements. Okay. So the first relationship between these two, and again, this epsilon we can actually replace this epsilon with 1 over m. Okay, so if we do that, that means we can also set this limit of xk equals to x, k to infinity is equals to intersection of, okay, we are saying 1 over m, so that means, okay, then all the integer, positive integer m. So maybe I'll put different color. So you can see everything are exactly the same. It's just that we just replace epsilon with 1 over m. So 1 over m larger than 0. So it's going to say that m is greater or equal to 1. Okay. Alternately, we can have this. Okay, so now you get this idea. Okay, so next things, then we know this. Yeah, maybe before that. So what is the complement of limit xk is not equals to x? So the complement for limit xk is equals to x. So complement, this one equal, so the complement will be not equal. Okay, so from here, then we can see that the collection of all the outcome whereby limit of xk omega not equals to x omega is equals to the complement for that. And from here, we know these two, okay, this and this. Then if we take the complement for it, and after that, by using the De Morgan's law, okay, so using De Morgan's law, okay, so I'm not going to express the two. Then we can have this identity. So this is equal to this. Maybe we just look at this. So this is equal to intersection, union, intersection. If you take the complement, so you have to switch all this operator here. Then I'm going to have limit of xk not equals to x, k to infinity will be equals to, if you take complement, so this will become union, union will become intersection, intersection will become here. And this is A will become not A. This. So I'm used back D, so this will be epsilon larger than 0, n greater equals to 1, k greater equals to n, epsilon. So this will be equals to this. Alternately, we may use this, we may change epsilon to 1 over m. So this one can also be expressed as this union of m greater or equals to 1 okay, instead of omega, epsilon, so we replace with 1 over m. Okay, so this is the first relationship that we need to use. Okay, anyway, by the way, so this is actually equations 5.2 in the lecture notes. Oh, no, this one I think it's the same. Should be this one. They are same. So equation 5.2 in the lecture notes. So this is the first thing that we need to know. Right? Okay, the next thing. Also, remember this, recall from, I can't remember when, from previous lecture, I don't know which lecture, so I have discussed this before. So if you have this one, the union of K, okay. Okay, I think this way. Okay, so from our previous lecture, so we have this actually. Maybe we can say this is epsilon. It doesn't matter. Epsilon or over m is equals to. Okay, if we take union, so this is actually equals to set of all supremum of this. Okay, so that is the relationship over here. So you may interpret this statement in this way. So in a way, you can see supremum is equivalent to say that is equivalent to maximums or the largest. Okay? In a way, it is not really true, but the greatest. Okay, it's not really true, but you may say it is it's a sort of like a equivalent to say that as the greatest supremum. Okay, so and remember the example that I saw. So if you said if you were your eldest, if you say your eldest brothers is older than me. Okay. Okay, maybe I'll say you can put it this way. If I say your eldest, you may interpret in this way, your eldest brothers or is older than me. Okay, so that means the supremum means the greatest or the eldest. So among your siblings, the supremum larger than epsilon, larger than me. So if your eldest brother is older than me, so that means this is actually equivalent to say that. So at least one of your siblings is older than me, right? So this is equivalent to sort of that. So when you talk about at least, so like what we have discussed just now, when we talk about at least, so which is actually relate to union. Okay, so you may remember this kind of relationship using some simple logics like this. Right, so this is from our lecture. Okay, so you may look at the right hand side, then you get it. So the supremum of this larger or equals to epsilon will be equal to union of this. Okay. So similarly, maybe just questions. See whether you can. Okay, maybe just a simple exercise. Let's say I have an exercise. Okay. So how about this one? Now I'm using supremums, right? What happened if I change to infimums? So infimum of K for something, maybe ZK, okay? is larger than 0. So this is equals to what? Fill in the blank here. Fill in the blank here. So what is the answer? So think about it. So the answer A and K, B. So what is the answer? A or B? Go and think about it, right? So in a way, increment will be the least, the smallest. Okay, the smallest. So you may just revise this. How to interpret this statement? So let's say you may put, say, increment stand for smaller. So your youngest, not younger, youngest brother is older than me. What does it mean? Okay, think about it. So which one you should use? And or union or intersections. Okay. Right. This is not what we want to use. Okay. So for today's lecture, we only need this. This one. Just remember, union of this thing will be, we can supremum of this. Okay, so then you can see this one, 5.2. So this is what we can have. This is a union, so we can form 5.2. So from 5.2, we can have this limit of xk not equals to x is equals to union. Yep, union of okay, we actually have two. We can either use epsilon intersections, then supremum of k larger equals to n for xk minus this larger than epsilon. So alternatively, we may replace epsilon with 1 over n, so it can be also expressed as m larger than 1 intersection of okay, so we just do it slowly. So from equation 5.2, so you can proceed to these equations.
At this point, does it matter whether the soup is in or out of the curly bracket?
Can you please repeat and speak louder, please? Like, sorry, maybe sorry.
Does it matter if the soup is in or out the curly brackets? Hello?
Sorry. Some issue with my internet, so our campus internet. Okay, can you repeat your question once again?
Yeah, does it matter if the soup is inside or outside the bracket?
Does it matter if the soup is inside or outside the bracket? Does it matter? Yeah, before that, am I still sharing?
Yeah.
I'm still sharing, right? Okay. Yes. In a way, you can say yes, or you can say yes, or you can say no. Okay. How should I can I answer this question after the discussion of this?
Yeah, sure, right. No problem.
After the proof, you remind me again to talk about these things, right? Yeah. So whether the soup is inside or outside doesn't matter. You may say yes or you may say no. Okay. So I will explain to you guys the difference. Okay. The soup that is inside the bracket and the soup that is outside the bracket, they are not the same. Okay. I will explain to you later. Okay. Okay. By the way, yeah, this is what we come to here. So this is still in 5.2. Let's say 5.2b. I will say this 5.2b. Okay. So now you look at this one. Okay. And now maybe you can forget about how. Okay. Yeah. That should be a K. Okay. You just focus to this part only. Okay. Or you may just focus to this part. Just look at here. So that means that that's the ends over here. Okay, so let's say if we just write this.
I don't think you're. Is it just me or you're no longer sharing now?
I'm not sure. Can you see my? Can you guys see my screen? I'm not sure whether I'm sharing.
No, we cannot see your screen.
No, right? Okay. Yeah.
We cannot see your screen,
so
Doctor.
Okay, yeah. I'm sharing again. Can you guys see it now? Hey, am I still recording? Sorry, because just now I was disconnected. I think I'm still recording, right? Okay, yeah. I'm still recording. Okay. You can see. Can you guys see my screen?
Yeah.
Okay, good. All right. Okay, so Adam, this is the same equation. It's just that I just how should I say it, sir? I bring this inside, become a super right there. So let's look at this inside here. So what we can do is, let's say we just simply write Cn to be this supremum of k larger than n, xk minus this greater or equal to epsilon or 1 over n, doesn't really matter. Okay, you can look at it. This one, which one is easier? Okay, like I said, this is actually can also be expressed as this way. I think maybe for this one, it will be easier to explain using this. Okay. Okay. So Cn is equals to union of that. So this is our Cn, union of something. So from here, then you can see that. So from here, you can see, because this is a union. How should I say? When n larger, so this thing is getting smaller and smaller. Okay, so you can see. Doesn't matter. I hope you guys can get a picture. So this thing will getting smaller and smaller. So this is a decreasing sequence of sets. Okay, the reason is here because of this is k larger than n, right? So if you can see C1. This is because of C1 is sort of like 1 union the second union the third one union the third one, the fourth one, and so on. And C2 will be the n will be 2 here, you are running index with k larger than 2, so that means we are begin with 2, 3, 4, and so on. Okay, so that's why from here we can see C is a sorry, I think the other way around. A decreasing sequence. Yeah. Right. So then we just need to go back to one theorems. So recall from theorem 1.4.3, okay, when C is a decreasing sequence, so then we're going to have the P of union of all the Cn will be the limit of P of Cn. So this is theorem 1.4.3. So this conclusion is applicable for either increasing sequence or decreasing sequence. Okay. Okay. Then we come back to this. So so this is what we can have. Okay. Now we can do this already. Okay. We take limit both sides. Sorry, not limit. We take the probability both sides over here. So we have this. The probability of limit xk not equals to x will be equal to the probability of, wow, lots of things, union of epsilon greater than 0 or 1 over m, doesn't matter, each can take either one. So n greater than 1 and the supremum. Right? Two main bracket, okay, one by one. So this is the supremum of k greater than n, xk minus x larger or equals to epsilon. So we have a bracket outside here. Okay. Okay, we have this is equals to this. Okay, now according to here, okay, from this theorem, and this is actually our Cn. So from our discussion above, so by using theorems 1.4.3, we can have this. The sorry, this is make a mistake here because this is a decreasing, so this is not union. This one's supposed to be intersections. Okay. Okay, so that means if you look at here, this is actually our Cn. This whole thing. Okay, this whole thing is our Cn here. Right. Okay, from theorem 1.4.3, then I'm going to have this. The probability of intersection of n larger equals to 1 for this supremum. Is equals to limits of n to this. Right, so this is from the above arguments here, so which is from theorem 1.4.3. So from this theorem 1.4.3, we can have this relationship. It's sort of like we can take out this intersection to outside that becomes limits. Okay, so but this is actually the probability for those which is inside here. Okay, but not excluding the union this. Okay, so this is what we can have. Okay, now all right, so maybe I could say this is our equations 5.3 here in our lecture notes. Okay, now we can prove our theorems. Okay, so first we left to right. So if we assume this xk converge to xas, so this is equivalent to say that the probability of limit of xk not equals to x is equal to 0. So we assume this. So if this is 0, so according to here, that means this one's 0. So that means the left hand side here will be 0. So that means the right hand side must be 0. So according to these assumptions, then we can have this from our 5.3. So we can have this, the probability of must be equal to 0. So this is equal to 0. Okay. And if you look at this, then we can have this must be less than this. Okay, I'm running out of space. Okay, maybe I do it step by step. I'm gonna rephrase my thing, sorry. I'm gonna rephrase my things. Okay. Maybe we start off with this one first. First, we have this, the intersection of n greater than 1 for this supremum of xk minus x greater than epsilon. So this is always subset to this union of or epsilon of this. Okay, so this is always a subset to these things, right? So I think this is clear. Okay, so this is always subset to this. So when we take the probability on both sides, this must be less than this. Okay, if we take probability, so this must be less than this. Yeah? Okay, now if you look at here from our hypothesis, we assume this is equal to 0. Okay, the probability of limit xk not equal to x is equal to 0, and also from our 5.3, this is just the left hand side for 5.3, right? So that means this right hand side must be equal to 0. So if we put it inside, then we can see that here. So from the hypothesis and 5.3. So we can see the right hand side must be 0. Or this bit must be 0. Okay, so the right hand side must be 0. So the right hand side 0, so that means this one must be 0. So the left hand side must be equal to 0. Okay, so that is, then we can have left hand side is equal to P of intersections of this. Is equal to 0. But from our discussion just now, so this one is actually just equals to limit n to infinity P of this. So primum of xk minus x greater than equal to epsilon to 0. Okay, so this is how we can get these statements here. Yeah, maybe just to write out the statement once again.
Sorry, doctor.
Yep.
I want to ask, how do we get the left hand side equals to 0? I for the left hand side part.
Oh, okay. So it's actually here. This is the left hand side. So this is the right hand side, right?
Yes.
The right hand side is with 0 probability. So this left hand side must
yes.
be with 0 probability, right? So this one must be left hand side or right hand side. Okay, maybe I should say.
Oh yeah.
Make it clear. Sorry. I think I should say clearly. This is a star, right? So then I think it's clearer. I should put a label for it. So my bad. So I should have said right hand side of the star is equal to 0. If right hand side of star is equal to 0, so I must have the left hand side of star must be also equal to 0, and which is just this one. So I got this as equal to 0.
Okay. Okay. Thank you.
Okay. So then come back to this is what we want to prove. Okay, this is what we want to prove. The propositions 5.1.2. Xn converge to X almost surely implies this is 0 for all X. Okay, just again. So what does it mean by almost surely? So this is actually equivalent to say that the probability of limit x k not equals to x is equal to 0. So just now we have assumed this, then we got this. Okay, so that means this is how we can get this is equal to 0. So that's why we have proved this implies this. Okay, so this is how we can prove this. Okay, so the second part. Okay, so now we assume the left hand side, the right hand side is correct. So we assume this is true. So we assume limit n to infinity for p of supremum of xk minus x greater to epsilon is 0 for all epsilon. We assume this is true. Okay. So again, we just need to go back to our relationship up there. Where is our relationship? Okay. so this 5.3. Okay, so we come back to our 5.3 here. So this is our 5.3. Oh, I'm using color. Okay, now we read. This is our hypothesis. We assume this is equal to 0. So this is our 5.3. So we do not want this. So in 5.3, we can see that the probability for this one not equals to x is equals to this one, right? So again, as I said, we can always replace this epsilon with 1 over m. So in other words, we can also assume, we can also replace this with 1 over m. Okay, so instead of epsilons, so we may replace this with 1 over m. So 1 over m. So for all n larger or equals to 1. Okay, they are actually equivalent. So like same as here. So instead of epsilon, so we may replace this with 1 over m. So m larger than 1 and 1 over m. So this is what we can have. Okay. So this is from 5.3. So this is equals to it. Okay, maybe just to let you know what we want to prove. Okay, so we assume this. We want to prove xn converges to x almost surely equivalent to say that the probability of limit xk not equals to x is equals to 0. We want to get these conclusions here. So I think this part is more easy. So this is equals to this. And by using the Boy's rule, so this is actually less or equal to summating all the n, the probability of this. Okay, so this is less than this. And like what we have explained just now, so this is actually equals to limit of p of supremum of xk minus x equals to 1 over m. So this is what we have. But from our hypothesis, we assume this is equal to 0. Okay, we assume this thing is equal to 0. So in other words, all this must be equal to 0. Okay, so that means this is actually less than sort of like 0 plus 0 plus 0 plus and so on. So which is equals to 0. Okay. So again, the right-hand side is equal to 0 and the left-hand side is smaller than right-hand side. So the left-hand side must be equal to 0. So this must be equal to 0. Right, so that's the end of the proof of propositions 5.1.2. So Okay, anyway, just to let you have a look once again, the statement for these propositions. Okay, so here's the statement. This statement said that xn converge to x almost surely if and only if I have this. And according to maybe I state the definitions, then you can have a picture for it. Okay, and then instead of saying the definition, maybe I would say, so this is from our definitions. So definitions 5.1.2, it said that xk converge to x almost surely. So if and only if the probability of limit xk not equals to x is equal to 0. So this is equivalent to this. This is equivalent. So that means is that these two are equivalent. So from here, then we can see that these two are equivalent. So I have this p limit of xk not equals to x if and only if limit of p of supremum of k xk minus x larger than epsilon equals to 0 for all epsilon. Okay, so this is the case. Right, so actually the proof is quite difficult. It's very long. So the reason that I include the proof over here is actually I want to use this proof as an example to demonstrate or to give you a revision about several ideas. Yeah, so maybe just look at the idea that's the technique that we have used here. One by one. Okay. First of all, this is one very useful, useful theorem. Okay, we have actually used it quite often in our previous lecture. Okay, that is theorem 1.4.3. Okay, I hope by using after this proof you have some idea when to use these theorems. Okay, so C1 is a decreasing sequence of events or increasing sequence of events. Then we have this P intersection of Cn is good limit of PCn. If Cn is increasing, you just replace this with union. So this is a first technique that we have used here. And the next one will be this. Okay. The next one will be this. So another techniques here. Okay. You can always sort of like depends on you, not always relate. So supremums larger, or maybe you can use this concept. How should I say? Maybe you can follow this concept. Supremum and then larger than this, that will be related to union. Okay. So if you are not sure, not always union, it depends on the situations. Yeah. So what if you're not very sure, maybe you can follow this kind of examples. Okay. If this kind of analogy, then you should be able to get the answer. So this is one answer, right? So for example, if you look at it, what is the answer for it? Okay. So if the infimum of xk larger than 0 is equivalent to union or intersection here. So you look at this, the left-hand side. So this is actually, you may relate this to our statements here. So you relate this. Infimum is sort of like the smallest, okay? Smallest larger than 0. So just imagine if your youngest brother is older than me. So the youngest one is older than me, so that means all your siblings must be older than me, right? So that's why the answer will be okay. So that's why the answer will be this one. Okay, answer will be so this one. Got it? This is the way. So this is a second technique that we have used here. And I think this is actually from the limit from calculus. Okay, so actually this is the things that we have used here. Right. Okay, maybe let's go through another result. Okay, so which is quite important. Compared to this, this is an equivalence relation, equivalent conditions. Unfortunately, if you look at this criterion, there's limits involved here and supremum involved here. So sometimes it will be quite difficult for us to compute this value because it involves limits and it involves epsilon. Involve supremum. So not that easy to use. Okay, so for practical usage wise, so this is not a very good criterion to be used. So that's why it will be better we replace with another I simply call it workable conditions. Okay, so that is the next result. So this one. Propositions 5.1.3. Okay, so I think this is a better conditions for it. Unfortunately, if you look at here, the statement here is if then. So which means there is only one direction, not two directions. So the reverse direction might not be true. So you can see this is comparatively easiest to be used because of its in what do you call it? We don't have to compute the limit. We just need to look at the summation, the series. Okay, so let's come back. The proof is actually quite straightforward if we know some of the known result. So before that, just come back to this. Xn converge to X almost surely. Maybe up here, just look at the relationship for the above three things. So here, Xk converge to X almost surely. Okay, is equivalent to say that. Oh, I think, sorry, this is something missing. I will say this one equals 0. Is equivalent to say that. Oh, okay, so this is 0. P of limit xk not equals to x is equal to 0, right? And P of limit xk not equals to x0 is equivalent to say that limit of this one is equal to 0 for all epsilons greater than 0. I can't remember what. Okay, sorry, I can't recall what is the number for it. Okay, maybe just look here. Okay, so you can see, so these three conditions. So this is the first one. Okay, this is the second one. This is the third one. 1, 2, 3. Yes, these three are equivalent. So this one implies this. So that means I want to prove that this one will imply these conditions. So to prove this, so we just need to recall this one. Sorry, I can't remember I can't recall where's the numbering for the theorems. So, okay, maybe I refer to it first. So where is my book? Okay, yeah, I got it. The Borel-Cantelli lemma. So again, just recall this. Recall we have this Borel-Cantelli lemma. So which is in chapter 3, lemma 3.1.5. Okay. So this Borel-Conte, look at the first one, number 1, the Borel-Conte lemma said that if you have a sequence of events, so if the summation of P of AK is less than infinity, so this will imply that P of limit supremum of AK is equals to 0. So this is our Borel-Conte lemma. Okay, now by using this Borel-Conte lemma, so we can prove our theorem propositions 5.1.3. Okay, so we assume this is 0. Xk minus x greater than epsilon is less than infinity for all epsilon. N equal, so k less than n. Okay, so we can write this one to be our an. Okay, so according to the first Borel-Conte lemma, if the sequence of PAK is less than infinity, we can have the probability of limit supremum of AK will be equals to 0. Okay, so then we just simply put this one to be our an. So that means this is less than infinity, then we can have by this Borel-Conte lemma, we can have 0 is equal to probability of limit supremum of xk minus x greater than epsilon is equal to 0. So again, because of this is a decreasing sequence, then we can have this. So this will be equals to limit of this. Okay, maybe I do it step by step for you guys. Okay. Okay, so we have this, right? And limit supremum is actually equals to P of limit n to infinity. Just now, as I this is a intersection union, so union of k greater than n of this event. Okay. So again, you may check this like our previous discussion. So this is actually a decreasing sequence of events. So that means we can actually take out this limit n to infinity of P of this. Okay, this is equal to 0. Okay, so how to get this? So this one refer to again theorem 1.4.3 and our previous discussion just now. Okay, using this theorem and this. So then from here, then this is how we can get it. So this is why we can get limit of P supremum greater than this is 0. So then from these conditions, then we can have hence our xn converge to x or more surely. So this is another example to apply this Borel-Conte lemma. Okay. All right, so maybe we come back to our previous discussions. The answer for the question, supremum. So here we have two different supremum. Okay, we have two different supremum. Okay, the first one is supremum. What should I say? Supremum of a sequence of numbers, right? So the first one, or maybe I don't set numbers. Okay, doesn't matter. I think numbers of value are the same, right? Or scalar, or values. Okay. What? How should I say? Okay, maybe I would say. Okay. Scalar value. Okay, I just said values. Okay, I think you guys are understood. This is understood, right? Okay, so the first one, we can have a concept supremum of a sequence of value, means numbers or scalar. Okay. Values, you may interpret or numbers or scalar. Okay, so this is the first concept of supremum, right? Supremum of a sequence of value, right? So examples, we can have a supremum of n greater or equal to 1 for what number do you like? Maybe n squared over n squared plus 1. So from here, you can see the one inside here. This is a value, right? Okay, so we have a first concept of supremum. So we have a sequence of value. So we are looking for the sort of like largest value, but not really true, the largest value for it, something like that. Okay. So secondly, we also have another idea of supremum. Supremum of a sequence of events. Yeah. Okay, in general, it might not be events. It's supposed to be set. Okay. However, over here we only interested on events, so that's why we can set event, right? So you can see that two different value. Get it? Supremum of this. So examples. You can say a supremum of n larger than 1 for maybe you can say let's say you look at the interval 0 to n. Okay. So there are two different ways. For the second kind, it's much more easier when we say supremum. So this is actually, I think you guys got the actual idea, right? So this is actually just simply means supremum is equal to the union of all the n from 1 to infinity. Right? You get the picture? Okay. One is a supremum which associated with numbers or value. The other one will be the supremum corresponding to events set. Okay, so don't mess up. Okay, now we come to these things. Okay, let's look at our case here. Usually, when we put this x n greater than 0, so this is actually a set. Am I right? It's an event, or at least it must be a set. Okay, so this is a set, right? So this is a set, but xn is a scalar value function, right? A random variable is always a scalar value function. Okay, so that means when when you talk when you apply the supplement to the xn, so it will be the supplement for the first kind. When you put the supplement outside, will be the second kind. So that's why then you can see that's the difference. So then number one, when we say supplement of n larger than 1 of this. So this is, in this case, so this supplement will be here. This is the supplement for set. Okay, so this is actually just equals to union of n equals to 1 to infinity for this set. Okay, so but when we come to here, when we have this supplement of xn larger than this, so that means this is actually the supplement for, this is the supplement for scalar. Right, so they are not the same. Okay, I hope you can get the ideas. Huh? So because we are using the same shorthand, SUV, supplement or infirmament. However, they are applied to two different type of object. Right? So I hope you can get a picture for this. Huh? All right. So, wow. Okay, just nice. So we have 5 minutes to 7:30. Before we take a break, so you have any question about the previous lectures or our previous discussions?
Are we discussing tutorial 4 later?
Tutorial 4. Next week. When did I discuss the tutorial? Last week, is it?
Huh.
Did
last
I discuss
week?
the tutorial last week?
Last week was tutorial 3.
Oh, last week. Okay. Because we have discussed the tutorial last week, right? Next week we will discuss tutorial 4. Okay. As usual. So next week, if you have any, you may raise the questions before the lecture, so that I can focus on those questions that you want me to discuss, right? Okay. So after this, I will continue to section 3, right? Am I right? Okay. So let's take a short break. Okay. Next. Sorry. Any question? Good. No question. Okay. Next, we come to sections 3. Am I right? Forget it. I can't remember the numberings. Next, we're going to discuss the center limit theorems. Okay. All right. So let's take a break. So as usual, we continue our lecture at 8 o'clock.
Doctor.
Yeah.
Sorry. Can I have a short question? You
sure,
know
sure.
the definition of a simple random variable.
Okay.
They say the AI events constitute a partition. So does that mean that is disjoint?
The definition for random variable.
A simple random variable.
What page is this? In the lecture notes.
Oh.
Okay, never mind. Definition. You are talking about the definition of random variable or the simple criterion?
The simple random variable.
Simple random variable. Okay. What's your questions?
So the definition, it has like the indicator function, and then it has the AI. So the AI is the event. They say it constitutes a partition of the sample space. So does that mean that it's disjoint? If they use the term partition, does that automatically mean it's going to be disjoint?
Yes.
Yeah, actually, yeah, that was it. Thanks.
yeah, when we say let's say A1 up to AN form a partition. Okay, so for omega. So when we say partitions, right? Yeah, it's always means two of them means first they are destroyed. So I think you guys know the meaning of destroyed, right? So that means mutually exclusive, destroyed, and B. First they are destroyed, and secondly, if you are taking the union of all of them, so will be equals to omega, just like that. That's the meaning of partition, two of them. These two, as long as they fulfill these two criteria, so we can say they're form of partitions. Yeah.
Okay, thank you.
Okay, no problem. So okay, so I guess I can stop here now, right? All right, so I'm stop recording. No problem, right? Okay. Okay. So let's